Right. So today we're gonna dive into something pretty wild.
Yeah.
We're talking about vehicles that can survive falling back to Earth from space.
Oh, yeah.
I mean, think about it.
Uh-huh.
These things are hitting the atmosphere at like ridiculously high speeds.
Many times the speed of sound.
Yeah, and the heat.
Yeah.
I mean, it would just vaporize.
It's unbelievable.
Most things.
Yeah, it's a real testament to, human ingenuity that we can even pull this off.
Yeah.
The conditions are just so extreme.
Totally.
It really pushes the limits of what we know about, materials and aerodynamics.
So that's what we're going to try to unpack today.
Yeah, let's get into it.
In this deep dive, we're going to, try to understand the core principles.
Yeah.
The real fundamentals.
The fundamentals.
That make this kind of engineering possible.
Absolutely.
We've got some cool stuff to work with today.
Yeah.
We've got this really detailed design project. Okay.
From some aerospace engineering students.
Right.
Aparna Ojha, Samuel Robertson, Ayush Kool, and Somesh Puri from Hindustan University.
Cool.
And then we've got another student design.
Okay.
This one's for a 4-person re-entry vehicle.
Nice.
And this is from Parth Singh, Basant Mohammed Abdelminam, Mohammed Shakir VK,
all right,
and Dasari Ramakrishna.
Got it.
Also from Hindustan University.
Interesting.
So we're getting the student perspective, kind of a fresh take on things.
Absolutely.
And then to round things out, we've got this study on re-entry vehicle systems.
Okay.
Prepared for the Department of Transportation.
All right. So we're getting a broader view.
Exactly.
Yeah.
Yeah. So we're kind of getting a little bit of the new stuff, a little bit of the, the well-established.
That's a good combination.
Yeah. So hopefully by the end of this, you'll have a really good grasp
of what it takes to build one of these things.
Definitely.
So let's start with the basics.
Okay.
What happens when a spacecraft starts to come back into the Earth's atmosphere?
Yeah, so when that spacecraft begins to descend, after being in space, it slams into the air.
Right.
And the air is getting denser and denser.
Right.
And it's going so fast that it creates this thing called a bow shock.
A bow shock.
Yeah, think of it like a boat going through water.
Okay.
At supersonic speeds.
Okay. Yeah.
Creating a wave.
Yeah.
That's essentially what's happening.
With air.
Yeah, with air.
Okay.
And this rapid compression, that's what causes the deceleration.
Right.
It's a braking effect, and it also generates a ton of heat.
Yeah, when you say a ton, I mean, we're talking like melt steel kind of heat.
Yeah, extremely high.
Yeah.
It's incredible.
Yeah.
And on top of that, that heat actually strips electrons from the air molecules.
Okay.
Creating this thing called a plasma sheath.
A plasma sheath?
Yeah.
What is that?
So it's like a layer of ionized gas that surrounds the spacecraft.
Okay.
This plasma can actually block radio waves.
Oh, wow.
Which can cause a communication blackout.
So they lose contact?
Yeah, temporarily.
Wow. So that's got to be like
It's a little nerve-wracking for the people on the ground.
Yeah, absolutely.
For sure.
So the reports were mentioning some speeds.
Right.
That sounded pretty crazy.
Yeah.
How fast are we talking when these things are coming back?
So when a spacecraft is coming back from low Earth orbit, it's usually traveling at around 20,000 kilometers per hour.
Okay.
Which translates to about 17,500 miles per hour.
Okay, so that's got to be...
That was fast.
Some kind of Mach number.
Yeah, it's about Mach 25.
Mach 25.
Yeah.
I mean, I don't really know what that means.
So Mach 1 is the speed of sound. And that speed changes depending on the altitude and temperature.
Okay.
But at sea level, it's about 12,235 kilometers per hour.
Okay.
So Mach 25 is 25 times that.
So 25 times the speed of sound.
Exactly.
Wow, okay.
Yeah, and the report mentions that anything over Mach 4 is considered hypersonic.
Okay.
So that includes airplanes, missiles, and these re-entry vehicles.
Right. Okay, so it's not just spacecraft coming back from orbit that have to deal with this.
Yeah, so think about like the first stage of a reusable rocket.
Okay, like a SpaceX rocket.
Exactly.
Yeah.
When that comes back down to land, it goes through a re-entry phase as well.
Oh, really?
Yeah, and they have to use those aerodynamic control surfaces.
You mean like the fins?
Yeah, the fins.
Okay.
To manage the descent.
Okay.
To slow it down and to steer it.
So it doesn't burn up?
Exactly.
Wow.
Yeah, they have to navigate this thing called the re-entry corridor.
The re-entry corridor.
Yeah, it's like this sweet spot of altitude and speed where they can slow down safely without burning up or bouncing back out of the atmosphere.
So it's like
It's a tightrope walk.
It's a very narrow window.
It is.
Wow. Okay, so we've got this thing screaming back to Earth, generating all this energy.
Right.
What forces are we actually dealing with here?
So the main forces are gravity,
Okay.
which is pulling it down,
Yeah.
drag,
Okay.
which is the air resistance,
Okay.
and then lift, which can help control the vehicle.
Okay.
And the report points out
Yeah.
that initially, drag is the biggest force.
Okay, so
Yeah.
like if you stick your hand out the window of a moving car,
Exactly.
that's drag.
Yeah, just amplified like a million times.
Wow. Okay.
Yeah, it's the force that's trying to slow the vehicle down as it moves through the air.
Okay.
And to understand drag,
Yeah.
we have to get into some aerodynamic concepts.
Okay.
The first is the drag coefficient.
Drag coefficient.
Yeah, or Keat.
Okay.
So this basically measures how aerodynamic something is.
Okay.
How easily it moves through the air.
So like a lower seed means less drag.
Exactly.
Okay.
Think of a teardrop shape versus a flat plate.
Okay.
The teardrop is going to move through the air way easier.
So if you had like a brick versus like
a really sleek.
Yeah, like a pointy rocket.
Exactly.
The rocket would have a much lower seed.
Yes, exactly. And the drag coefficient is affected by a couple things.
Okay.
So there's skin friction.
Skin friction.
Yeah, so that's like how rough the surface of the vehicle is.
Okay.
Like if you rub your hand on something smooth versus something rough.
Okay, yeah.
So that's kind of like that.
So a rougher surface?
Yeah.
More drag.
Exactly.
Okay.
Then there's form drag.
Form drag.
Yeah, and this is all about the shape and how it disrupts the airflow.
Okay.
And then for vehicles that are designed to generate lift, there's also lift-induced drag.
Lift-induced drag.
Yeah, and then for complex shapes, there's interference drag.
Interference drag.
Where the airflow around different parts interacts.
Okay, so this guide is kind of like...
Yeah, it's like a score.
The vehicle's drag score.
Exactly.
Okay.
Lower is better.
Lower the better. Okay.
Yeah.
So what's next?
So the next big one is the ballistic coefficient.
Ballistic coefficient.
Yeah.
Okay. What's that?
So it's often abbreviated as BC.
BC. Okay.
And this tells us how well an object can overcome air resistance.
Okay.
So it's basically the vehicle's mass divided by the product of its drag coefficient and its cross-sectional area.
Okay.
So BC equals M divided by C times A.
Okay.
So a higher BC means less deceleration for a given drag force.
So like a bowling ball versus a feather.
Exactly.
The bowling ball has a way higher BC.
Much higher.
Okay.
And it's not affected by air resistance as much.
Okay.
So if you drop them both, the bowling ball hits the ground first.
Okay.
Obviously.
Right. So higher BC,
yeah,
you can punch through the atmosphere.
Yeah, initially, further.
So can we actually calculate that force of drag?
Absolutely.
Using the CD?
Yeah. So the drag force, which is written as F drag, can be calculated using the equation.
Okay.
F drag equals 1/2 times roon times V squared times seed times A.
Okay, break that down for me.
Well, so roon, that's the density of the atmosphere at that altitude.
Okay.
V is the vehicle's velocity.
Okay.
Seed is the drag coefficient, which we talked about.
Yeah.
And A is the cross-sectional area.
Okay.
So the area that's facing the oncoming air.
Right. The area that's getting hit by the air.
Exactly.
Okay.
And the report breaks down each part of that equation.
Okay, cool.
And then there's also lift, which is generated perpendicular to the direction of motion. Airflow over a surface.
Okay.
So this is really important for those lifting body designs that we'll talk about later.
Okay, cool. So we're starting to understand the forces and the motion involved.
Right.
But let's talk about the design.
Let's get into it.
Of these vehicles, what's the top priority?
So the main goal
Yeah.
is to safely get rid of the spacecraft's kinetic energy.
Okay.
As it comes back into the atmosphere.
Right, it's going super fast.
Yeah.
Gotta slow it down.
It has to slow down to a complete stop at a specific landing site. And it has to do all of this without putting too much stress on the vehicle.
Right, or the people inside.
Exactly.
So we have to dissipate this energy
Yeah.
without destroying the thing or hurting anybody.
Yeah. It's a delicate balance.
It sounds impossible.
It's challenging. But that's what's so cool about it.
Yeah.
So the reports really highlight how interconnected everything is. So you have the aerodynamics, how the shape interacts with the air.
Yeah.
You have deceleration, how quickly it flows down.
Right.
And you have the trajectory dynamic.
Okay.
So the path it takes through the atmosphere.
Okay.
And the engineers have to design all these things to work together.
Wow. Okay, so the shape.
Yes.
Seems like it's super important.
The shape is crucial.
Okay.
It determines the ballistic coefficient.
Right.
Which, as we said,
yeah.
affects how the vehicle responds to air resistance.
Okay.
And it's also important for generating lift,
right.
if that's part of the design.
Okay.
And the drag coefficient seat
right.
is really dependent on the shape.
Yeah.
And it's actually very difficult to predict seat accurately.
At those speeds.
Yeah, at those speeds.
Why is that?
Well, because the conditions are so extreme.
Okay.
We don't have a lot of wind tunnels.
Right.
Can replicate Mach 25.
Okay.
So the engineers have to rely on computer simulations.
Okay.
Things like computational fluid dynamics or CFD.
CFD.
Okay.
Yeah.
And they also use Newtonian flow.
Newtonian flow.
Yeah, which is a simplified theoretical model.
Okay.
That can give them some estimates.
Okay, so it's basically like using computers.
Yeah.
To figure out
exactly
what the air is going to do.
Right, because we can't really test it in the real world very easily.
Right. Okay, so the shape affects how the vehicle moves and how it slows down.
Absolutely.
So what are the trade-offs?
So if you have a more streamlined shape, like a higher BC.
Higher BC, okay.
It's going to slice through the atmosphere more easily.
Okay.
And it's going to go deeper before it experiences the maximum deceleration.
Okay, so that sounds good.
Yeah. It means it spends less time in the upper atmosphere.
Okay.
So it reaches the ground faster.
Okay.
Which can improve the landing accuracy.
Oh, because there's less time for wind and stuff to push it off course?
Yeah, less time for atmospheric disturbances.
Okay.
But the downside is that these streamlined shapes experience higher heating.
Oh, no.
Concentrated at the leading edges.
Oh, so it gets really hot in one spot.
Yeah.
Okay. And that could be a problem.
That can be a big problem.
Yeah.
Because it can overwhelm the thermal protection system that's protecting the vehicle.
Okay, so what's the alternative?
So a blunter shape with a lower BC.
Lower BC, okay.
It's going to create a detached shock wave ahead of the vehicle. And this shock wave acts like a buffer.
Okay.
And a lot of the heat gets dissipated in the air between the shock wave and the vehicle.
It's like a shield almost.
Yeah, kind of.
Okay.
So this spreads the heat load over a larger area, which results in lower peak temperatures.
Oh, okay. So less extreme heat in one spot.
Exactly.
But there's got to be a downside.
There is.
What is it?
So blunt vehicles decelerate more rapidly.
Okay.
Higher with the atmosphere.
Okay.
And they spend more time there.
Okay.
So predicting their landing spot can be a bit trickier.
Okay. So it's like this balancing act.
It's a constant trade-off.
Between heat and deceleration.
Deceleration and accuracy.
Exactly.
Wow.
Okay.
Yeah.
So the report also mentioned the different subsystems. So what else do you need?
Right.
Besides like the shape.
So beyond the aerodynamic shape and the heat shield, you need control systems.
Control systems.
Yeah. So if the vehicle is meant to maneuver, it'll have aerodynamic control surfaces.
Okay, so like flaps.
Yeah, like flaps or fins.
Okay.
And then there are attitude and spin control systems.
Okay.
To make sure it stays in the right orientation.
So it doesn't flip around or anything.
Exactly.
Okay.
And then there's a deorbit propulsion system to actually start the descent.
Okay.
In orbit.
All right. And then, of course, the structure itself.
Yeah, the structure has to be strong enough to handle the forces.
Yeah.
Then you have power systems.
Okay.
Power interface units to manage the electricity.
Okay.
And, of course, tracking and communication systems to stay in touch with mission control.
Right. So we've talked about the shape being super important.
Yeah.
And the report mentioned a few specific shapes, sphere sections, sphere cones, and lifting bodies.
Exactly.
So let's go through each one.
Okay.
What's a sphere section?
So a sphere section is basically just a part of a sphere.
Okay.
Very simple shape.
Okay.
It's inherently stable.
Okay.
So if it gets nudged, it'll go back to its original orientation.
Okay. As long as the center of mass is in the right spot.
Exactly.
Okay.
But a sphere doesn't generate much lift on its own.
Okay.
But if you fly it at an angle, called an angle of attack, you can generate some lift.
Okay.
And that gives it some cross-range capability.
Cross-range capability.
Yeah, so it can steer sideways a bit.
Okay.
And that widens the reentry corridor.
Oh, okay.
Yeah, and the report mentioned that this is the shape that was used for some of the early capsules.
Like Mercury.
Yeah, Mercury, Gemini.
Yeah.
And Apollo.
The classic capsule shape.
Exactly.
Yeah.
They were simple to analyze and build.
Right, back in the early days.
Yeah.
Okay, what about a sphere cone?
So a sphere cone is basically a spherical segment combined with a blunted cone called a frustum.
Okay.
And this shape is generally more stable than a sphere section. And if you design it right, it can maintain stability from the moment it enters the atmosphere all the way to impact.
Oh, that's good.
Yeah. And the report gives examples like Galileo, the probe that went into Jupiter, and Stardust, which brought back comet samples. But early sphere cone designs sometimes stayed in the upper atmosphere too long.
Oh, really?
Yeah, because of their aerodynamic characteristics.
Huh. Okay, so what about lifting bodies?
So lifting bodies are specifically designed to generate lift.
Like wings?
Yeah, like an airplane wing.
Okay.
And this allows for much greater maneuverability during re-entry and a longer flight path through the atmosphere.
All right, so more control.
Way more control. And they can land more precisely. And they have a greater cross-range capability.
Okay, so they can go further sideways.
Yeah, basically, they're more like gliders than falling capsules.
Right, okay, so then the report also mentioned specific spacecraft like Soyuz and Shenzhou.
Right.
Where do those fit in?
So Soyuz, the Russian spacecraft, uses a sphere cone design.
For the part that comes back?
Yeah, for the descent module.
Okay.
Which is covered in a heat shield.
Right, to protect the cosmonauts.
Exactly.
Okay.
And Shenzhou, the Chinese spacecraft, has a similar design.
Okay.
A 3-module design.
Okay.
With a heat-resistant descent module that also uses a sphere cone shape.
Okay, so sphere cone seems pretty popular.
It's proven to be very reliable and effective.
Okay. And then the report had this table comparing a bunch of different vehicles. Shenzhou's Apollo, the Vozdvesheny Apparat capsule, and even the SpaceX Dragon.
Interesting.
What's interesting about that data?
So if you look at the Soyuz descent module, it has a mass of about 2,950 kilograms.
Okay.
It's about 2.24 meters long.
Okay.
And 2.17 meters in diameter.
Okay.
And the internal volume is about 3.5 cubic meters.
Okay, so that gives you a sense of the size.
Yeah, it's pretty compact.
Yeah.
Especially considering it has to hold people and equipment.
And all their stuff.
Yeah. And if you compare that to the other vehicles, it shows how the designs are influenced by what they need to do.
Right. Different missions need different vehicles.
Exactly.
Okay, so let's talk more about the aerodynamic design.
Right.
And the report mentioned how challenging it is.
It is.
For manned missions.
Yeah, because you have to think about the G-forces on the astronauts and the temperatures.
You don't want to cook them.
Exactly.
Okay.
So the aerodynamic design isn't just about getting it back to Earth.
Right.
It's about keeping the crew safe.
Yeah.
And the way the vehicle interacts with the atmosphere determines how strong those G-forces are.
Right.
And how much heat the shield has to handle.
Okay, so it affects everything.
It affects everything.
Wow.
It's really the foundation of the whole vehicle system design.
Okay.
It affects the mission planning.
Yeah.
The performance evaluation. The vehicle control.
Okay.
And the structural loads.
Right.
It's a big deal.
Okay. And we keep coming back to the BC.
Yes.
Yeah.
The ballistic coefficient.
And the drag.
And the drag.
So what's the takeaway there?
So the report goes back to that drag equation.
Okay.
To really emphasize how important it is.
Okay.
For understanding how the vehicle slows down.
Right.
And like we said before.
Yeah.
A blunt body design is often the best choice.
Okay.
When you need to decelerate quickly.
Okay.
And minimize that peak heating.
Okay. And that's because a blunt ship creates more drag.
More drag.
And that shockwave.
And the shockwave
helps deflect the heat.
Exactly.
Okay.
But of course, that larger surface area needs to be covered with heat-resistant materials.
Right.
Which is what the student project focused on.
Right. Okay, so let's talk about materials. Materials. What are we using
to build these things?
To build these things to keep them from melting.
Exactly. So the report talks about a bunch of different materials.
Where? Hit me.
So there's aluminum alloys.
Okay.
For the structure.
Why aluminum?
It's lightweight.
Okay.
And strong.
Makes sense.
Then for things like optical payloads.
Okay.
They use special glass.
Okay.
With synthetic resins.
Why?
So they can see through the heat.
Oh, wow.
Yeah, it's pretty cool.
Okay, then there's carbon fiber reinforced polymers?
Yeah, those can handle really high temperatures.
Okay. How high?
Up to like 2,300 degrees Fahrenheit.
Wow.
Yeah, so they're good for leading edges.
Okay.
Wings and nose caps.
Okay.
They're strong and light.
Okay.
But they can be a little brittle.
Oh, okay, so there's always a trade-off.
There's always a trade-off.
Okay, what else?
So then there's ceramics.
Okay.
which are good for heat resistance.
Up to a point.
Up to a point.
Okay.
And then there's nanomaterials.
Nanomaterials.
Yeah, those are really interesting.
Okay, why?
They could potentially be much lighter.
Okay.
And they could perform better.
Okay.
At high temperatures and under radiation.
Wow.
Yeah. The report suggests they could even save weight compared to the traditional materials.
Wow.
But they're expensive.
Okay.
And difficult to manufacture.
Right.
So it's still early days for those.
Okay, so still being researched.
Yeah.
Okay.
There's also Inconel alloy 625.